Hello. In this lecture, we are going to look at ballistic projectiles. So we are going to consider the scenario where an agent needs to throw or launch a projectile at a target, and this target could be stationary or moving. We might also need to consider other situations like, does gravity affect the projectile? Do we have drag? What other conditions could affect either the projectile or the target? So our agents sometimes need to be able to fire these projectiles, and we need to figure out a way to get the agent to aim such that the projectile ends up at the right place. Now, these are ballistic projectiles. That means that in terms of the simulation, the projectile is picking up all of its velocity in one single time step. So in real life, a ballistic projectile is accelerated over a very short period of time, and then there's no further acceleration, at least in terms of setting the trajectory, the initial velocity. Now, the projectile could change velocity over time, but usually that is because of gravity, or perhaps drag would be affecting the projectile as well. So it's easy to simulate Newtonian physics with particle dynamics or rigid body dynamics. These are things you're probably already familiar with from high school physics, calculating based on different equations, or maybe even working with calculus to actually derive these equations. So it's generally easy to simulate Newtonian physics, but solving for intercepts is not always easy. So we've sort of tackled this problem to some degree before. You may recall from the steering behavior lecture, we introduced pursue. Pursue was a predictive seek. So trying to find the right path to get our agent to a moving target. And the way that that algorithm was approached was to use an approximate heuristic, and that was really motivated by minimizing the computational cost, because this is something that we're calculating over and over every single frame. So this could easily take up a lot of our computational resources, especially if we have many agents and they're all needing to do the same sort of pursue calculation. So the way that this worked was we would determine a time that the intercept would occur. So we solved for t, but did so in an approximate way. And the way it worked is we figured out, well, what's the distance from the agent to the target that's moving, and based on that distance, for that relative vector, the magnitude, we could divide it by the speed at which the agent's going to move. So we would assume, just like going full speed ahead, what's the maximum speed the agent can go? We'll assume that is the case for the whole trip. So this doesn't take into account that the agent might be heading away from us, or sorry, the target heading away from us or towards us, or the agent. And we're just coming up with an approximate approach. So the length of that relative position vector, take the magnitude, divide it by t, or sorry, divided by the velocity will give us t. Now that we have that t value, we extrapolated the target's movement. So the target has a current position. We can add to that current position velocity of the target times this estimated t. So that'll tell us a future position of the target. The agent that's chasing or pursuing can then just seek to that future position. So we're only using an estimate again because we don't need it to be precise. We're focused more um, on it being efficient and just generally getting us closer and converging on the correct solution. But in the case of a ballistic projectile, we only get to set the velocity one time, and then we have no longer any programmatic control over that velocity. We have to just let it continue course. Perhaps if there's gravity will be acting on it, but there's no intelligent adjustment like, say, a homing missile, which would use basically pursue or something similar to pursue in the calculation. So we need to spend more time making sure our calculation is correct because we only have this one chance if we have any hope of it being correct. So you might think of projectiles like grenades or footballs that the agent will be launching at a target. And of course, those scenarios are ones where we would want this precise velocity determination for this ballistic trajectory. But there's also other scenarios you might consider as well. One might be for a character that moves on the ground. So, for instance, in the Spider-Man universe, there's a bad guy Rhino, and when he gets angry trying to attack Spider-Man, he charges forward. So if you're making a Spider-Man video game, you might want to implement Rhino so that he fights for a while, then gets angry, and then charges towards Spider-Man. But Spider-Man tends to be moving around a lot, so it's not going to be very helpful or very challenging gameplay if Rhino just heads to the current position of Spider-Man and stays on that course for the run. So for gameplay purposes, we might have Rhino use a ballistic trajectory intercept along the ground to try to head off where Spider-Man's currently running, as a player, say, controlling Spider-Man and moving. But then we'll take away Rhino's ability to correct course or maybe limit it significantly. So you can only change a tiny bit. And so that would make it challenging for gameplay. So the player would see that Rhino is charging towards them and then would know that they need to change direction and make some sort of evasive maneuver. But you don't want Rhino to have the ability to constantly update to a new velocity, new heading, because it would be impossible to get out of the way, perhaps. So, all these rely on some fine-tuning of speeds and various parameters of the movement. But you could very well need a ballistic trajectory, a precise calculation for that sort of gameplay. So sometimes it's straightforward to solve an intercept. So for instance, if you have a target that is not moving at all, it's just a fixed target, and your projectile has constant velocity, so there's no drag, there's no gravity, you can just set it in motion and it goes forward. This might be like in outer space, perhaps, so launching a projectile with no gravity, and the target's not moving. So if you have that sort of situation, it's really easy to calculate. It's similar to the pursue algorithm. You just need a relative position vector that will allow you to get the launch direction, because you can normalize it to a unit vector, and then you can multiply it by your desired projectile speed, and that will give you the full velocity of the projectile. So you can just set that velocity on the projectile and let it go. So here I've got a little shooting gallery app. This is a pre-recorded video. This is a demonstration of the algorithm I just described. So it's just like 3 lines of code or so to fire this projectile. Gravity is turned off. So normally Unity defaults to having gravity on, but in this case it is turned off. You can see what looks like some curvature to the path, but the way the shooting gallery works is that there's a randomly moving shooting position. That's the yellow cylinder sliding up and down, just kind of randomly moves. And it's actually similar to like the Wander algorithm, but just limited to one dimension. And then it's calculating as if the target is fixed. Of course, you can see the target, the red sphere, is in fact moving, but it's moving so slowly that the projectiles are still able to hit in most cases. And you can tell that it's off a bit because the green projectiles are hitting on the backside of the target relative to the direction the target is going. But this is, you can tell, is accurate, just simple algorithm, and it works well if you have this sort of a scenario. There's just not a lot of degrees of freedom in terms of the solution we're trying to determine. But what would happen if gravity did affect the projectile, or the target is moving or moving fast enough? So the more degrees of freedom that we would allow, the more complicated the system of equations that we would need for solving will get. Eventually, the equations can get so complicated that you can't even directly solve them anymore. Or if you can, it becomes overly complicated, or it's prone to errors. Like maybe you have to break your solutions up in lots of nested conditional logic, and easy to mess things up. So we can see how our simple solution fails pretty badly when we add some effects of gravity. So that right now the projectile is still moving pretty slow, but gravity, so it was hitting it a little bit right there in the middle of the video, but clearly it's not aiming high enough. It could potentially hit the target, but the fact that it's not taking into account the effect of gravity means that this is not a very effective algorithm for that purpose. So we will be looking at some methods for solving more complicated projectile scenarios. And there's 2 general methods that we can use for solving these ballistic projectile launch velocities. The first is to directly solve, and we've seen an example so far of directly solving for a trivially simple example. But we are going to see much more complicated examples, or a couple at least, in the rest of this lecture series. So we'll be setting up a system of equations and then solving, finding a precise intercept time, and then applying that to our motion equation for our target. And then that, since we were solving for the time of the collision, plugging that into the target movement, we know that the target, after having moved by whatever amount it does in t units of time, that's going to be the same position that our projectile is going to arrive at. And so that allows us to work backwards from that point using the equation for motion of the projectile to ultimately figure out what's the initial velocity. Again, that cannot always be done. So we'll also look for how to deal with more complicated scenarios. And that would be a situation where we're going to want to use an approximate approach, which we will refer to as iteratively solving. So this, at a high level, works by estimating a reasonable solution, and then we'll figure out how far off it is. Then we're going to refine the parameters of the equations until the solution is close enough to the desired outcome, should a valid outcome be possible at all. So, in order to use an iterative solution, um, we must be able to model the projectile and target movement according to defined parameters. In some cases, we can directly solve the position of projectile and target with some, say, if we knew a t value, a time of intercept, we could plug it in. It's not always easy to solve that t, but in some cases, it's not even easy to solve where a projectile is at any given point in time. There's actually another level of simulation where the current position is dependent on the previous position. And so we have to iteratively solve the position of the particle on top of iteratively solving our adjustments of parameters. So that makes things doubly hard. And we'll revisit that issue. But next up, we will discuss firing at a projectile at a static 3D target position, but the projectile will be affected by gravity. So we're going to address the issue that we just saw in the last video where the projectile was failing because of gravity. All right, we're going to look at launching a projectile that's affected by gravity, launching it towards a target that's fixed in position or static target, and it's going to be a 3D position. All right, so again, assume that we have 3D positions. So our projectile is, the launch position is in 3D, the projectile is going to move in 3D, and then we're trying to hit a target, but this target is not going to be moving. And the projectile, again, is affected by gravity, but we're not going to support drag. So it's just particle dynamics without drag. So the typical sort of movement where you consider velocity and acceleration for the projectile. So we'll have the initial velocity and the acceleration due to gravity. We're going to assume also that the projectile is always going to be launched at full force. There's not going to be any attenuation of the amount of force applied. So that's going to simplify things a bit for us. And so really all we're solving for is the direction of the velocity, because we already know how much we're scaling by that being the maximum speed at which the projectile is going to be launched. So have some definitions for variables here. We have P sub t, the position of the target. Again, this is stationary. The initial projectile position. We have a vector u, which is for the direction of the projectile at the launch. So this is the direction part of the velocity. Then we've got the speed, which is just a scalar. So the scalar times the u sub p, that will give us the full velocity. And then we've got gravity, and we are also concerned with a time value. So T sub c, time of collision. So what we're going to be doing is solving for vector u sub p, and that is the initial direction of the projectile at the point that it's being launched. So at the point that the projectile is gaining an instantaneous change in velocity. That's the ballistic part of the trajectory. So from particle dynamics, we have seen before that you can figure out the position, future position of a particle based on the amount of time elapsed. If you know the initial position, you know the velocity, so it'd be original position plus velocity times time plus 1/2 acceleration times t squared. Our acceleration is gravity. The gravity vector, it probably will just be the y component of the 3D vector is going to have like negative 9.8 meters a second, or it could be other values as well. Our velocity, in this case, we're replacing the v with our u vector, which is direction, so it's a unit vector, times the s, which is the speed of the projectile. So it's the max speed of the projectile. Multiply that times u, and that will give you velocity. So that will be times time. So this equation should be familiar. And we could break it apart into 3 separate equations. But we have unknowns for the u vector, which includes our ux value, the uy value, and the uz being a 3D vector. So that makes 3 values or 3 variables. And then there's also a fourth one we don't know, and that's the time of collision. So that's the problem because we've got 3 equations so far. So we need a 4th equation to be able to solve the system of equations. And so luckily we do have one, and we can get that from the fact that we know something about our u vector, and that being that it is a unit vector. That means that its magnitude is equal to 1. So using the equation for magnitude, we would know that that would mean that the square root of the sum of squares of the x, y, and z terms, that would be equal to 1. Of course, since we've got the equation set equal to 1, well, we could just take the square of both sides and know that that the 1 will just stay a 1. So we can just get rid of the square root, which is a nice thing to do generally in anytime you're trying to compute a solution with a computer. You want to get rid of those square roots. All right, so we go back to our equation for motion, being able to solve a future position of the projectile based on the initial conditions and the elapsed time. So we want to solve for u. Again, that is the direction that we are launching our projectile. So we can isolate our u vector, and we'll get what's shown on the slide here. So you've got the position of the stationary target minus the initial position of the projectile, or the launch position, and then minus the half gravity times time squared over speed times the t. So we can substitute for the that relative position vector. So the p sub t minus p sub p, which is that again being the target position minus the initial projectile position. Subtract this, that gives us the delta, and so that just cleans up our equation a little bit. That will help us in the future here. We can plug into each dimension of the u vector into that fourth equation. If you recall, we had the magnitude of u is equal to 1. So we can break that down knowing that it's the sum of the squares of the x, y, and z terms. Since we've just now solved for u, we can extract the x, y, and z terms. As shown here, I've only got the work shown for the x term, but it's going to be exactly the same with the y and z. Just the subscript is going to change for what's being referenced. So in this case, like, we would have the direction, the initial launch direction squared for the x term would be the x term or the delta minus 1/2 g, the x term of that, times the time of collision squared over speed times time of collision, and then the whole thing squared. So if we expand all those terms, then you get what's shown on the next line. And so you'll see that it's a big mess of terms here. So we can do the exact same thing for y and z. Again, it'll look the same It's just going to refer to a different of the three dimensions of our vector. So one thing that is interesting to note here is that we were working with vectors, but the fact that we have our u vector, we're taking the magnitude of it. That means any of these vectors we're plugging in, they are going to reduce from the three dimensions down to a single scalar dimension, and that's going to be because the fact that we're taking the magnitude here, that makes all of keeping track of the x, y, and z, that all disappears the same way it would if we were just plugging directly in three values for u. That means that like our delta, which is a vector, and g, those are also going to become just a single value once we're through with everything. All right, so we're now at the point where we've got 1 equals the fully expanded terms, and we've got that denominator, the speed squared times time squared. So we can move the denominator out because we have a common denominator for the three terms. So we pull that out and then multiply both sides. So now, rather than 1 on the other side of the equal, we've got that denominator. No longer a denominator, but the speed squared times time of collision squared, and that's equal to all those terms. Now, we could have stayed in vector form rather than expanding or separating out the x, y, and z like we've done here. And I'll just go back in the slide. So when we pick that fourth equation, we know that the magnitude, the 1, is equal to u p x squared plus, like we could have just left it as the vector u magnitude equals 1. So let's see, get back to where I was. So let's see how maybe that can make sense with things that we know about vector operations. So you probably heard of the dot product, but don't think about dot product just yet. Let's instead think about, well, what if we were multiplying two vectors just in general? What would it mean to multiply two vectors? So don't think in terms of any matrix operations, which certainly matrix operations can help with manipulating vectors, but let's just think of vectors as being equations. So we might represent vectors in unit vector form. So we take the basis vectors, and so the x term of our vector would be times the basis vector for the x-axis, which would be I with a little hat on it. So I itself is a vector. It's a standard basis, so we'd have a 1 in the x position, and then a 0 for the y, and a 0 for the z. So we've got, say for vector r, we'd have r sub 0 would be the x term times I plus r sub 1 times j, and r sub 2 times k. So that's the unit vector representation of the vector r. We can do the same thing with s. So we have the s sub 0, s sub 1, and s sub 2, but paired up with the I, j, and k. So we could just expand, like do like a polynomial expansion, so multiplying combinatorially all the terms. So this is like when you when you have three terms rather than, you maybe remember like FOIL, first, outside, inside, last, but in this case we have three terms, so we just have to brute force go through all of the different pairings as we multiply out. And so you'll end up with some terms like r sub 0 I times s sub 0 I. So you have a whole set that are matched, like an I unit vector times an I unit vector with associated coefficients. But there's also some here that are mismatches, like I and k, or j and k, and so on. Evaluating all these terms is like doing an outer product, but the fact that we have orthonormal basis vectors for our Euclidean space, so that meaning like the I unit vector is 1, 0, 0, the j is 0, 1, 0, and the k is 0, 0, 1. Well, when you would be multiplying those, they're 90 degrees relative to one another, and therefore they just go to 0. So the only terms that are interesting when you're multiplying the unit vector form is only going to be what's called the inner product. And so if you actually laid out the multiplication of all these terms, so which would with matrix multiplication, which I believe would be R matrix multiplied by S transpose. So that would give you a matrix with all of these terms in a grid, but only the diagonal would have potentially have non-zero terms. And so that's the inner product along that diagonal. So we get down to the point where you have R sub 0, S sub 0, and then I times I, R sub 1, S sub 1, J times J, and R sub 2, S sub 2, K times K. Now, so far we've just been thinking of this as multiplication. And so this is where things get interesting. So if you actually try to continue this expansion with the I unit vector times I, or the j times j, or the k times k, what you would have is, well, you could, the basis vectors are themselves vectors, so you could do the exact same thing we just did with this kind of polynomial style expansion. And so that would be in standard basis, the I unit vector could also be represented in standard basis, which would be 1 times I plus 0 times j plus 0 times k. And so you could multiply them, but you could keep always defining what's inside the next level with more basis vectors. So we're like we're at this point where we've got infinite recursion if we just continue to follow that line of reasoning. But it clearly you're going to keep getting the same thing over and over. There's no progress being made. But as you recall, we were plugging into, if I go back slides, we were plugging in to the magnitude. So we're replacing these the u terms, the unit vector u that's referring to the direction of our launch. All of these terms, whether they involve vectors originally or not, because it's a magnitude, it's all collapsing down into just a single scalar value. So we started with 3D vectors, but now the 3D vectors are becoming the single dimension. So in this case, the dot product is a way that we can collapse down. So a dot product is kind of like multiplying, but when we get to this point, we can just use the dot product. So now in that case, we have like a terminal condition, because we know that the dot product of two unit vectors is always going to be 1. So we replace the I dot I and the J dot J and the K dot K. Each of those we can replace with 1, because we're performing the dot product. We no longer need to isolate our terms separately according to dimension. We're just going to collapse it all into a single dimension. And so that means that what we were originally calling R times S is really, it's a dot product, R dot S, because we know that we're collapsing everything down to this single dimension. So that gives us just the dot product of the two vectors. So that's the x term of the left vector times the x term of the right, plus the y of the left and the right multiplied by each other, plus the z term, left vector times right vector, and then sum all of those. That's what a dot product is. Now, the dot product There's lots of other uses for the dot product, such as finding angles and performing projections and so on. But um, we have this notion of how to handle um, like in an equation for representing a vector, like that we just did when we were substituting in for the vector u. We have a way to handle multiplication. Now we can also look at, well, what if it's the same vector times itself? So I did the same thing with the outer product. We know that the mismatched unit vectors are going to cancel out to 0. So we're only left with the inner product. And we could just say that, well, it's just a dot product, r dot r, and we know how to handle it. But we can also notice that the magnitude of r, if we were performing the magnitude operation, that would be, of course, what you're familiar with, the square root of the sum of squares of those three terms. And that looks an awful lot like if we took the dot product of r dot r, because that we're at r sub 0 squared plus r sub 1 squared plus r sub 2 squared. And if we look at the magnitude, well, underneath the square root, or the radicand, we've got r sub 0 squared plus r sub 1 squared and r sub 2 squared. So it's exactly the same thing. So if we square both sides so that rather than the magnitude is equal to the square root of the sum of squares, we can say the magnitude squared is just equal to what was the same as our dot product. But this is useful for like concise substitution purposes in representing our vector. So if we go back to that big mess of terms that we had before, where we had performed the substitution in our u vector for the three separate dimensions for the x, y, and z. I'm only showing the x, so it would be 3 times as long as what's shown here. But if we shuffle our terms around, we will get to the point where we'll recognize, say, for the vector delta, we've got the square of the x term, the y term, and the z term, squaring each of the terms and then adding them up. And so that can be, if you look where my mouse is here, we can just say the magnitude of delta squared, and then minus, well, when we're considering the fact that we're multiplying the gx times the delta x, but we do that for also the y and the z, that's the same as a dot product. And if we'd left it in vector form to begin with, then we would see that when we perform the square root, or sorry, the square before we did the square root for the magnitude, when actually the square root disappeared, so we just had the square, we know that the g vector times the delta that you're going to get when you perform the polynomial expansion. Well, when you see the need to multiply g times delta, that's really, we just are going to use a dot product. And then also we've got a similar thing where we had a g vector times a g vector for the gravity. And so again, that's going to be the magnitude squared. And so all of these different approaches, these are all things that are familiar. We can just, in terms of like later when we actually need to calculate these in code, well, we'll just take the magnitude of a vector and then or we'll take the dot product. So it makes the implementation a lot more concise, and potentially we can optimize things. If you have efficient implementations for these. So we have this more concise representation now, sticking with this vector form and operations performed on the vectors that will collapse down to single terms because of either dot product or magnitude. But we want to set this all equal to 0 because we're trying to get to the point we we ultimately want to know u, but we also need to know t, and so t is going to help us to actually solve for u. So that's what we're trying to do now. So we're trying to solve for t. So the time of collision t sub c, we currently would see that to the power of 4 and a power of 2 term that is involved. But we're gonna move the term is on the left side of the equal side over, so it's all set equal to 0. And this, we're basically setting up for using quadratic formula. And so in fact, that's what we'll do. Now we have maybe not the familiar form that you're used to in the simplest examples of quadratic formula. So we have the time of collision to the power of 4 rather than to the power of 2. But we don't have any odd numbered powers in this equation. We have a t sub c to the power of 4 and a t sub c to the power of 2. We can just replace, rather substitute. We can substitute for t sub c to the power of 2. So we'll make like an x that is equal to t sub c to the power of 2. So that's going to give us like an x squared term and an x term. So now suddenly we've got everything in the form that we can easily pull out coefficients and set up the quadratic formula. So we do that, and so that means that it's actually t sub c squared is equal to the quadratic formula, plugging in all the correct terms. Don't forget about the plus or minus. So we're actually solving for potentially 2 t's, which we'll get back to that. But then we can now get rid of the square on our t sub c by taking the square root of both sides. So we actually have nested square roots. We have an outer square root and then an inner square root of this entire thing. But what this allows us to do is solve for 2 possible t's. Even though we're performing all operations on all these vectors, we know it all collapses down to a single scalar or one-dimensional value. So in terms of implementation and using these t values to finally solve for u, we look at the inner radicand. So that was the second or the inner of the 2 square roots. If that if the value under the square root, the radicand, if that is less than 0, that would suggest an imaginary number. We don't want that. So that would not be a valid solution for either. So if we go back and look, even though there's 2 possible solutions, if we've got that inner square root, if that equation there is less than 0, then we know the whole thing is an imaginary, and so therefore we just say, well, that throw is impossible. And that would be, well, you can see the gravity terms in there, and so that would be like the gravity is too strong to allow the projectile to ever reach the static target, would be the reasoning there. The other thing is, if either candidate time of collision is negative, you'll discard each and possibly have none left if that happened. So at that point, you would just return that the throw is impossible. So then typically what you do is that you'd set up like a method that returns true or false on whether the throw is possible. If it returns true, there's also some out parameters of the function call, or multiple returns, and that would include, say, our u vector, probably also like the time of collision that was used in the calculation would be useful. So otherwise, if you have 2 valid solutions, take the smaller one, because that's going to be better in terms of like gameplay. The quicker the quicker projectile to hit is probably the most useful one. You might have some reason otherwise. So for instance, one later in time will tend to have more of an arc to it. So maybe that would be worth considering. So you might revise the implementation if that's needed. Otherwise, if you only have one valid solution, of course, that's the one that you would use. And then in terms of code implementation, you don't want to repeat any expensive computations more than once. So you're going to carefully analyze all of these terms, look for which are terms that are have repeated use, and only calculate them once. Use some memory, save a variable. So if we go back and look, well, I see the gravity vector dot product with our delta. That appears a couple times. We've got some squared terms like the speed squared. Well, you don't want to have unnecessary multiplies any more than you have to. We've got these magnitudes that involve squaring. Well, so the magnitude squared. So you're not going to have the square root, but you're going to have the square of the XYZ terms for the gravity vector and delta. So like you want to avoid those sort of repeats. Also, you have the plus and minus. That means that you're calculating like t sub c 0 and t sub c 1. And they all have the same terms. It's just the sign of this plus or minus here is different. So of course you're going to want to cache across the two attempts to solve for t as well. All right, so once you have your t value, go back a few slides and you'll recall that we do have the equation for motion of the projectile. So again, that is a function of our velocity, our gravitational acceleration, and also the t value. The t, we know it now. Assuming a solution was found, we've got a good t to use. We can just plug that in. And well, first we'll go back to isolating our u vector because that's what we're trying to solve. But so isolate u, then we can plug in our t and all the other information that we know, and that will give us the solution for the direction of u. And then as far as launching it in our game, we can just assign our velocities, instantaneous velocity change according to the u direction times our speed, so the speed of the projectile. So set those up, and then of course in terms of simulation, we might have a physics engine that'll just automatically handle applying the acceleration for us. Or we would just need to maintain this information. So the projectile will need to maintain the statics and the kinematic. So that would be, we need to track position and velocity, and then the gravity for our game affecting the projectile. So that would be updated each frame. Now I've got an implementation. I'm going to show you a video here. This is my version of what I just showed you. And by the way, that equation for 3D projectile aimed at a static target with the effects of gravity, that is in the Millington Game AI book. So you might want to refer to that as well as this lecture. So here, of course, I've got the target is moving, but it's moving so slowly, it allows me to kind of visualize lots of different positions. So this particular software, the shooting range, this is something that's part of the prison dodgeball assignment. And it's just like a little test bed. So you can test out the algorithm that you're implementing for your minions to throw the dodgeball. So this is a good way to test. So having this target move so slowly, it's a little bit off. You'll actually notice that the green projectiles are hitting kind of on the back edge of the target, but it still lets me quickly see and debug and also demonstrate here what's happening. And of course, you can tell that an appropriate arc is being applied to the projectile so that it can hit the target. So yeah, this demonstrates that we're solving correctly here. And as long as that projectile is moving slowly enough, we can still get the hits. The physics simulation is being handled by Unity. So they leverage the PhysX library that is licensed from NVIDIA. So NVIDIA has developed, or they bought the company that developed, and they continued to refine that physics engine. But it's just doing some simple Newtonian style physics updating. Now the projectile is not under the effects of gravity; it's just moving along a random trajectory, but it's constant velocity, and so it just goes back and forth, bouncing against like an invisible wall. Now here is the same algorithm aiming under the assumption that the target is static. Now it's moving at full speed, and you can see that it's not very successful. It's always aiming to a position that's well in the past by the time the projectile gets there. So yeah, that's a problem, but we can potentially still make use of this. Of course, if truly the target's not moving, it's useful. We'll also see later how we could use an iterative algorithm. So we've got this approach. In terms of pros, it solves directly for a 3D target position with gravity affecting projectile. So that's a big step up from what we've seen before. The downside, of course, is it doesn't handle moving targets. But otherwise, this is definitely a useful ability for aiming that we'll see with incremental. When we add this incremental sort of refinement, we will be able to handle moving targets. Okay, next up, we are going to look at how to solve for a ballistic projectile intercept with a moving target. So previously we had a static target, but now we're going to change the problem such that we have a moving target. All right, so we saw with the static target solution, it worked well for that purpose. But in order to handle a moving target, well, we could continue to work with that algorithm and then implement an iterative solution around the static target solution. But first, let's consider actually directly solving for a moving target and if that is reasonably possible. So we're going to have to simplify the problem in order to get this to work. So we're going to have to go to 2D, and if we are to apply this to, say, like a 3D sort of scenario, well, we're going to have to project it all down onto the XZ plane. And so we'll have 2D vectors for positions and velocities of both the projectile launch position and the target's initial position, and the velocities. So also, we're going to say that the target and the projectile are going to move with constant velocity. Our projectile is not going to be affected by gravity. Of course, this is in 2D and it's in the XZ plane, so we're basically ignoring gravity. And for the projectile, we only know the speed, and we're calculating for launching at full speed. So we'll later see that we can actually, even though we're restricting this to 2D, we will be able to come up with useful solutions to the ballistic trajectory for 3D as well. But there will be some caveats, so we'll wait and see about that. All right, so some variables. We have initial positions for both the target and the projectile. And that's because both of them are moving. This is only going to be true for the very first part of the motion and the ultimate intercept. We also have a velocity, a known velocity for the target. That's a constant velocity, so no acceleration. Of course, there's the target speed as well, which would be the magnitude of the target's velocity. We have projectile speed. So this is how hard you're launching your projectile, the speed of the launch. Well, we don't actually know the direction. So we're going to be solving for the projectile velocity. And then we have, we have the time of the collision. So this is the time of intercept that we'll be trying to solve for, in addition to solving for the velocity of the projectile. All right, so we're going to rely on the law of cosines. So you might recall this from taking a trigonometry class. And so the law of cosines says that for a triangle with sides A, B, and C, where the angle between side A and B is theta, a squared plus b squared minus 2ab times cosine of theta is equal to c squared. All right, so we're going to use that, and also we're going to rely on the dot product as related to the angle between the two vectors you're taking the dot product of. So vector A dot B is equal to the magnitude of A times magnitude of B times cosine of theta. And it's also useful to know that if vector A happens to be a unit vector and also B happens to be a unit vector, A dot B is just cosine of theta. So we're going to leverage both the law of cosines and this dot product rule for angles as well. All right, so in order to apply the law of cosines, we need to assign equations to the edges of our triangle. All right, so for edge A here, the way that we've set up our mappings for the initial position, so we got the initial position for the projectile is on the left side, so the corner CA of the triangle, and then we put the position, the initial position of the target at corner AB, and therefore the length of edge A is going to be, well, we take the relative position vector between the initial position of the projectile and the target. So P initial target position minus P initial projectile position. So that's a relative position vector. We can take the magnitude of that, and then that will be that gives us a length for to assign to the triangle, so that when we can eventually plug this into the law of cosines equation. We also know that the speed of the target is equal to the magnitude of its velocity, and we can set up our dot product relationship to angles as the dot product of normalized form of A, which is a unit vector. So take that A, which again is the relative position vector, P initial position of target minus P initial position of projectile. Take that vector, normalize it to a unit vector. So that is a unit vector dot product, the normalized velocity of the target, and so that is also a unit vector. So with the two unit vectors dot product, we know that's equal to the cosine of the theta. So now we know the theta, the cosine theta part of the law of cosines equation. So we're starting to fill out this triangle here. All right, so next step, we'll use some particle dynamics, the displacement by velocity. So if you take a vector v times some amount t, then you know how much it moves in the x and the y dimensions. And we could also just figure out, the magnitude of this movement. So we could take the magnitude of vector v times t and determine the length of that vector rather than the movement in individual dimensions. So magnitude of a velocity is going to be speed. So in this case, the speed of the target times the time till collision. So how long is it taken up to the point of collision? So that's what our B is. And now we don't know the time of collision yet, but we do know the speed of the target. So we know that B is equal to this. So we're setting up a system of equations, basically. It's going to let us solve for this T that we don't know yet. Similarly with C, we know the speed of the projectile times the time it takes till collision that's going to be that length. So now we've got the whole triangle, all the terms needed we have now determined. So we plug in our A, B, and C into law of cosines. We get our A squared plus speed of target times T, square all that, minus 2 times the length of the edge A times the speed of the target times our T, and then recall the cosine theta, so we can replace that with the dot product of normalized vector A times normalized vector B, and all of that is equal to speed of the projectile times T, and that squared. So we can simplify all this, and we work our way down to the last line here, and we see that we've gotten everything into a form where we've got a T squared and a T, and we're now at the point we can plug into the quadratic formula. So we do that, and it is a similar scenario to what we had in the previous solution for the static target in 3D with gravity. A little simpler because we don't have the nested square roots, but we still have the same sort of concerns that we want to test the value that the radicand value, make sure it's not negatives, which would give the imaginary. Now we also need to check the denominator here because it's possible for it to be 0. We have, again, the plus or minus, so that means 2 possible T values. We want to, if we do have 2 valid ones, we're going to use the smaller of the 2. That means a quicker intercept, and you always want to favor the quicker intercept because we're making this assumption that say the moving target is moving at constant velocity. But in reality, if this is a game object controlled by a human player or another agent that we're trying to hit, there's no guarantee that it's going to maintain this constant velocity. It's a good heuristic, but it's a heuristic that rapidly becomes less and less likely to be true over time. So I want to keep that T small. And then another thing to look out for when you're actually implementing this in code, look for repeated calculations. There's some common terms like the normalizing of the A and the B vector, and then taking the dot product. You want to cache those values. You see that it shows up twice in the equation. You have the relative position vector calculation. So you've got just there's several terms here that you're going to be you're only wanting to calculate once because like there's multiplication involved, and that's those add up over many agents, many frames. If you're doing this over and over, you want to always look to write efficient code. You also have the plus and the minus, so don't forget that you're going to repeat terms that way as well. So cache that square root and use it again for when you're doing the plus or the minus version. All right, so you do all that, and well, you got a T value. We still don't know the velocity, and that's the important thing, right? Because that's what we need to be able to pass to our simulation to actually launch the projectile. So we're gonna set up name two new vectors here: the position of the target at collision and the position of the projectile at collision. Should be obvious that those are going to both be the same position, but the way we get there is coming from different directions. So we have the motion of the projectile, the motion of the target. But we know that at that one point, they're going to be the same. So the position of the target at collision is going to be equal to its initial position plus its velocity times time, which for a constant velocity object, that is what you would expect from particle dynamics. Now we also know the velocity of the projectile. Well, we know the initial point and we know the end point. We don't know the actual velocity, of course, but so we know the we know the relative position vector between the initial point and the final point. So we can divide that by t of the time of the collision. But that's not useful until we replace the final position of the particle in the equation. So that's shown in orange. So the replacement, we're using the position of the target at the collision. So you see where I'm mousing over. So we're just plugging that in for the final position of the projectile into the equation here. And then we can do that because we know this just by this scenario. We know that those two positions are the same, but the fact that they're colliding. So this substitution is valid. We can now simplify. So we got like the denominator canceling out for that term. Sorry, for the v velocity term. So we don't have a dividing by t here, but then we do have this relative position vector. So the position of the initial position of the target minus the initial position of the projectile divided by t, and then plus the velocity of the target. So that is our final solution. That's in 2D. Now, this equation that we have, so even though we're solving it in 2D, well, we could, so like we probably got here by projecting the x, y, z, assuming we're using this solution for a 3D game, we could just project everything down to xz plane and then work with 2D. But this final equation, we could actually treat it as 3D. There's nothing that would stop us from doing that. So we could plug it in. Now here's the thing that'll work. It's functional. You'll have a projectile that'll actually go and hit, but we've totally ignored any impact of the y direction on like distances and so on. So basically what the situation you have is we ignored the y, but then we suddenly added in. So it's very likely the magnitude of this velocity of the projectile, the initial velocity of the projectile we solved, it's going to be bigger than the maximum speed that we initially defined in the problem. That's quite likely. Now, this may or may not be acceptable in terms of your gameplay. Some games that'll be fine, and it kind of looks natural. It's sort of like something's farther away and up at an angle. The agent just throws harder because it's maybe more effort. Sometimes that's not acceptable, and you might want to actually impose the speed limit. Now, another thing, we could even not only go to 3D, but we could have 3D with gravity. And so to make that adjustment, we have to solve that when we're solving for velocity, we have to do it differently because we have a new equation for motion for the projectile. So we know from particle dynamics with the influence of gravity, you would have the new position would be the initial position plus initial velocity times time plus 1/2 acceleration times time squared. So in this case, we're going to have a gravity vector. It's going to include a sign, probably like in the y dimension, you're going to have like negative 9.8 meters a second squared. So we would have the position of the projectile at collision is equal to the initial position of the projectile plus velocity of projectile times time of collision plus 1/2 the acceleration due to gravity times the time of collision squared. So now what we can do is we can set that equal to the equation for motion of our target. So we take that, the right-hand side of that equation, and we're going to substitute again for the position of our projectile. We're going to substitute the final position of the projectile. Substitute in where is the target going to be after the amount of time elapsed for the collision that we've already solved for. So that'll be the initial position of the target plus the velocity of the target times the time it takes for the collision. So now we've got to shuffle terms around, just some basic algebra. We can isolate the velocity of the projectile. So we get this new form. So you can either use this form if you're not lobbing the projectile. It works for 2D or 3D. Again, with a caveat about 3D possibly throwing too hard. Or you can use this VP if you want the projectile to be lobbed, and it'll be a correct velocity, taking into account the gravity and still hit the target. But again, we still have this problem, probably to a larger degree now, that the magnitude of the velocity of the projectile that we just solved for is quite likely to be greater than the maximum speed that we had assumed at the beginning of setting up this problem. Again, that may or may not be an issue for your gameplay. So like I said before, when you have an agent, like say throwing a football or something, it looks like they're just throwing harder within reason. If you just keep if you don't impose any sort of limit, it can get ridiculous. I'll show you an example in a second, but it does tend to not look too bad in most cases. But you might have gameplay where it's really important to impose the maximum speed. So next up, I'm going to show you this in action. We've got a target that's moving at various speeds. We don't need to slow it down super slow to get our hits. And you can see that we are getting hits in 3D with gravity. This is cheating. This is throwing harder when it needs to. Right now, since it's throwing down, that's not as big of a deal. Again, this little shooting range just kind of randomly moves. So actually, I don't think I really have a good example in the video of throwing up. But there is at least a difference in height that's taking place. And you probably, if you paid close enough attention, you would notice that the speed changes depending on the relative positions there. So in this next video, I demonstrate this cheat problem that is occurring. So I modified here. Actually, it takes a little while to play out. So I think I've initially got the static collision solved. So I'm right on the edge. If you see, moving the manually moving the target. I found the edge of like a 45-degree trajectory with the static solution, so the previous video solution there. And then I changed algorithms. I switched over to law of cosines using the cheat method. So it just solves whatever it needs to solve. You see I'm dragging it further and further out. I'm well past the point that the static targeting was maxed out. It was returning false. It couldn't go any further. I'm having to zoom out because there's literally no limit here other than the size of the arena. And so it just adds arbitrarily much energy to the Y. So yeah, sorry, it's kind of small in this video, but hopefully you can tell like I've moved well past where the limit should be. The projectiles being sent at an incredibly high limit. But you could separately screen, you could just have like a cap, distance cap perhaps, like beyond a certain distance, even if the algorithm thinks it can come up with a solution, you just say, all right, that the overall distance between where the launch is and the projectile ends up, that it just went too far, and so you can just say, well, that was not allowed. And so in terms of this solution, using the law of cosines approach, it does solve directly for a moving target in 2D. And if you had to have a 2D game, it's great for that. You can still make it work for 3D, as we've seen. It does not impose a maximum speed in 3D, though. And it's not also, if you're using this for 3D game solutions, it's not ideal for extreme height differences or targets that are moving significantly in the Y direction. And so, like if you had a flight sim or a space combat game, it's not going to be ideal for that. You could make it work by choosing the best plane in 3D to project on. So not always projecting onto X, Z. You might project onto, say, X, Y, or Z, Y, or whatever, depending on where the game objects are, where the game object that's launching the projectile relative to the game object that is the target, and what's the closest plane that they're both moving in. So you probably come up with a little metric for that. But I would probably honestly would just use the prior solution with an iterative approach that we'll talk about in another video. One other thing I wanted to mention is that there's a kind of a trick you can do with the law of cosines. If you do want to impose a speed limit, you can use this holdback trick. And the holdback is basically, so you know what your maximum speed limit is. So when you call your algorithm for your law of cosines implementation, you pass it a speed that is like 90% of what you actually want to allow for. So that leaves a fraction of the total speed that can be applied in the Y direction, so any loft that you might need on your solution. So if it successfully finds a solution for the lob projectile in 3D, again, that the velocity is going to likely be higher than the limit you passed in, but it might not be higher than the holdback percentage. So if the launch point for the projectile and the position and movement of the target are roughly in the same plane, so there's not a big difference in height, this will work fairly well. So like if you have an enemy that's running on a flat surface and you have an agent throwing also on that same flat surface, this will tend to work fairly well. If there's extreme differences in height, like one agent up on a hill or right near the maximum limit, so close to where like the furthest your agent's going to be able to throw, not taking into account like a hill, throwing downhill or something, it's going to be a 45-degree launch angle. I'm sure you've worked these problems out before in your particle dynamics physics class before, but it's a 45-degree angle is the optimal for distance. This clearly, if you're only holding back 10%, that's not going to allow for a 45-degree angle. But if you hold back too much, the problem is what you end up with is you've reserved too much energy for Y, but the algorithm's only going to use as much Y as it needs, that little adjustment we made for the lob particle. So you end up with solutions throwing not as hard as they could be. So if you're trying to throw a projectile to like do damage, like a weapon, you're throwing soft. Your agent's going to be throwing soft, and that's not really what you want. You want to throw hard because you want to you want to do more damage, make it more likely that you're going to hit your target. So this is okay, but it's not the greatest solution. But again, that's only if you want to do like lobbed in 3D and truly want to enforce the speed limit. So we can look at the holdback version of law of cosines here. And so one thing you'll notice is, like if you look at the shots per second here, this has been running for a while. So this is already gone through 2,000 something hits. And the shots per second is averaging around 250. And that's pretty pretty low compared to when we look at well, if we went back and looked at the cheating version, that's the highest we'll see because it's cheating. But if we wanted to compare it to other approaches that limit speed limit, you'll have to look at the next video where we're going to use iterative approaches. But you'll see that this isn't competitive with the other approaches. But it also that this scenario that we're seeing is probably not where you would want to use the holdback version of law of cosines anyway. You would rather have like the movement of the target and the place that you're shooting from all be roughly in the same plane. In that case, it works a lot better. So like the assignment for the prison dodgeball, where you have the little minions throwing the ball, that's a lot more realistic for using this. Though I would even in that case recommend like an iterative solution, just to find as many possible solutions for when it's good to throw the dodgeball. But this is just interesting to consider because it is simple to implement. It's not as difficult as adding the extra iterative part. In this video, we're going to look at iterative approaches to solving ballistic intercepts. All right, so sometimes we can solve directly, but if we start to add more and more degrees of freedom to the movement of either the projectile, like adding acceleration, or the target has acceleration, or other types of movement, then we will create a system of equations that has a higher order polynomials, and will get difficult to solve. So we will maybe lose the ability to use the quadratic formula and have to use some other approach. And in some cases, that might not even be possible. So when things get more complicated than the approaches we've already seen for directly solving, you're generally going to want to go to an iterative solution. So we're going to look at a simple iterative approach using the static target solver that we looked at before, which had a fixed target in 3D. The projectile was affected by gravity. So we can use that in the following algorithm. It can also work with other ways that you might calculate as well. But so this is going to just leverage the static solver, but keep calling it more than once as a way to refine an estimate of a moving target. So the first step is you assume that the target is not moving, and then you solve for the intercept, find the t value of the intercept. And that t is going to be, for the static solver, the t is totally dependent on how long it takes for the projectile to get there. The target itself is not moving. It's because we're assuming it's fixed, at least from the perspective of the algorithm that we're using. But then what we're going to do is plug in the t that we just solved into the target's kinematic equation. And so that might be, say, with velocity and acceleration. So from particle dynamics, you would say your new your new position would be based on the original position plus initial velocity times time plus 1/2 of acceleration times time squared. So you plug that in, and you're going to get this new position for where the target is. So again, we're using this algorithm that's meant for static targets, and we're saying the target is in a new place now. So we take that new position, plug that back in to our algorithm in step 2. We just have this new position. So we're going to solve for t again. And t is, we're going to refine our t value. It's going to be some new value that reflects the fact that our target had moved. And so we do this again and then plug it again into the kinematic equation for the target. And the idea is that we should converge on a t. So the difference in the current t and the previous t will get smaller and smaller, or the difference in the position. In either case, we would expect both to get smaller and smaller. And so we're going to repeat this iterative process until a terminating condition has been reached. That might be just a depth count, like how many iterations. It might be that we're looking for some minimal change, or even combined these terminating conditions together. So like you say, the t value that we're calculating is only changing by just some little small amount. And that would be enough to say, okay, well, we're done at that point. So you typically would want to cap the number of iterations. So in like a video game, 3 to 6 iterations is fine. When running the algorithm, I've found it's useful to preserve the last good solution when you call the static target solver. You save the last good one. So when you iterate, so when you move the target forward, you might possibly move out of range, right? But if you're just on the edge of moving out of range, it could possibly still be a good opportunity to launch the projectile. And so if that is the situation, you want to perform a sanity check. So when you finally exit your iterations, if you had any good solutions at all, you can analyze it. You can plug in your intercept time that you solved into both the projectile and the target kinematic equations. That'll tell you where they both are at the same point in time, which should be a collision. But we can check for some minimum distance that might be, say, the sum of the radius of the projectile plus the radius of the target, if we can represent those objects with a radius. Keep in mind, we're aiming at an infinitely small point, like the centroid of the target. We don't have a way to aim at an area. We can only aim at a point. But just the way that this particular iterative solver works, we have this opportunity to check if we're close enough with our estimate. So that has this kind of nice bonus that we extend our range a little bit, because we can consider hitting a target right on the outskirts of the maximum range. Now, there's this other issue that if our very first attempt at solving in that algorithm, if I go back to the loop, so if the first visit to step 2 fails, we have nothing to work with. We don't have a t value to work with. So that's a problem. So the simplest thing is just to fail in that case. But in reality, the target could be moving at a fast clip towards the point that we're launching our projectile. If it's coming fast enough, it's possible our projectile could be fired immediately, like at a high arc, for instance, and then the target will come into range of the projectile that's now falling towards it and then get a hit. If we fell immediately, we're not going to catch that. So we might be able to adjust the algorithm to deal with this. I haven't attempted it myself, but it might be possible to, for instance, analyze a target that we could solve for the point of closest approach. And that would be a good sort of baseline to figure out, well, if we know the point of closest approach and we know the time of that closest approach, could our projectile hit that at with whatever speed we can throw at? Maybe we have to throw it at a high arc to get it to arrive at the right time. That might be possible. So So if you can solve for the point of closest approach, that that I guess would be the worst case. So that would at least allow you to sort of put a bounds on the potential to hit the target at all. So if you cannot hit at at that point, that would at least let you set a bound, so you might be able to look a little bit in front of or behind that point. So I haven't quite figured out exactly how to address this case of if your first attempt at refinement or setting the starting point for refinement fails, how could you deal with that? But I think the point of closest approach, something related to that would be useful. So here is a video of the algorithm I just described. So it's the static targeting. It's being applied to, with the iterative approach applied to a moving target, and the target is moving with constant velocity. So zero acceleration. We can see the metric here. I think I mentioned before that the text is incorrect. It says shots per second. Clearly that's wrong. It is 100 times the shots per second. But it's really the actual number is not really important because it's going to depend on the configuration. But it's the same settings for the different algorithms. All of these little shooting range scenarios are all using the same random distribution for the movement of the target and the launch point. So and also the velocity of the target is random as well. So we can see that like the shots that we're getting off this metric that we're scoring around a 500, it is it's a pretty good value. Of course, with the misses, we've got over 1,000 hits, 0 misses. So it's very accurate. In fact, you never see it miss. I've adjusted it so that it can hit the targets even on the edge of the range based on the sum of the two radius of the projectile and the target. So that extends the range a tiny bit to keep the score up. And so compared to like the law of cosines method that cheats, that allows arbitrary amounts of speed added in the y direction, that's the best, but of course it's cheating. So I think it got around like a 600, maybe a 700, somewhere in there for the shots per second times 100 metric that we've got here. So yeah, if you want to stick with a speed limit, this works pretty well. In fact, it's probably the recommended solution that you would use in most cases would be to use this approach. So in terms of the pros and cons of this algorithm, it's easy to implement. Not much code that you're adding on top of what you had to implement for just the static target solver. It's just a little bit extra. We saw the pseudocode a few slides ago. The cons, you might not be able to refine to a stable solution. You might actually have some instability. That could especially be around the point of closest approach to the target, because you're going to go from getting close to the target will be getting closer to, and then past the point of closest approach will be getting further. And you also might have problems like with accelerations where you have like direction changes that are caused by the accelerations. So I think those are the sorts of the sorts of scenarios where the refinement might have some trouble. This algorithm with using the static target solver and this type of refinement is going to tend to favor shooting behind the target. So that's not good for dramatic effect. You can have, like in a first-person shooter, say an enemy agent firing at the player is always going to be shooting at the behind the player, and therefore the player's not going to see with the first-person perspective. And so that's not good for dramatic effect. So, mentioned before, if the target is initially unreachable, but will be reachable in the future, then we might miss the opportunity to fire at them. So we do need like some special case logic to handle that, which isn't addressed here. And it doesn't work if our kinematic movement of the projectile and or the target, if that can't be directly just evaluated, say plug in a t-value and then figure out where it would be at a certain time, then we can't do that. So some equations for motion are actually incremental. Like you in order to figure out where it is, you have to evaluate it at incremental points in time. So that like the current state of the object is based on its previous state. You can't just directly jump to some arbitrary point in time. You have to actually simulate out the whole thing. And there are more complicated models, like some with friction, that where you would actually have to do that. So you cannot use this algorithm in that scenario. Next up, I've got an iterative algorithm for law of cosine. So you can also come up with an iterative algorithm to use with it. And that is so that we can properly enforce a speed limit. So this is a bit of a different approach than what we saw with static targeting algorithm. So we're going to start off, we're going to call the algorithm as normal with the full force, but let's say we're actually going to be solving in 3D. So even though it's a 2D algorithm, we're solving in 3D with gravity, let's say. So that means we're going to be introducing this y direction component. That's going to be cheating a little bit. We're very likely to end up with a velocity, the magnitude of which is greater than our maximum speed that we would like to enforce. So what we have to do is, we have to assess what that magnitude is. If it's too fast, then we want to run the algorithm again, but with a new maximum speed we're passing to it. So it's kind of like our holdback algorithm where we just had the fixed holdback, except now it's going to be dynamic. So we're going to pass a holdback that is halfway closer to the length of an optimal launch in the xz direction. So this would be assuming that if we were to throw at 45-degree angle, some of the energy would have to go in the xz direction, and some would have to go in the y direction. So we want the holdback to be halfway closer to that point. So wherever the current holdback is, what would be the optimal launch for our max S, not S holdback, but SP. So take a half step, and then we go back through the loop again, rerun the equation. Otherwise, if our velocity is not greater than S, well, there could be some different circumstances we need to consider. So one is that it's a very good match, and that would be if our magnitude of velocity is nearly equal to our max speed. So if it's approximately equal to the max speed, then that means we're throwing as hard as we want it to. Now we can't have it be exactly equal, because we're doing all this refinement. There's going to be we're not going to be able to converge perfectly on the maximum speed if any refinement has to actually occur. So that's where the 1 minus epsilon is coming from. So if say epsilon is 0.01, 1 minus 0.01 is like 0.99. So 0.99 times the speed. So we're just saying we're getting pretty darn close to the max speed. But we also want to make sure that we're not wasting energy in the vertical. And so we're checking to see if the S holdback that was last used, because this might actually be like several iterations in, the last holdback that was used, we want to check to see that it is greater than or equal to the xz that would be at optimal angle, meaning like optimal for distance, 45-degree angle throw. So if it is greater than that, the value for the optimal angle, that means it's a shallow throw, and that's good. We don't want to waste energy in the vertical any more than we have to, because that means we're just wasting time. We're pushing the t value out further unnecessarily, giving our target more opportunity to evade. We want it to be as low an angle as possible. But so if this overall criteria is met, well, it's good enough. We can exit and return this result that's nearly perfect. But if it is if it's too slow, so if that condition wasn't met, we can then check, well, okay, if it's too slow, that means that our the magnitude of our velocity is less than our maximum speed that we're trying to achieve. So if that's the case, then we are going to run through the loop again with a adjusted holdback speed. So we're going to use the previous speed plus half of the max speed minus the previous holdback. And so this will allow the algorithm to start to push towards a faster speed, basically. Now, the other thing, if it wasn't too slow, it might be that it's wasting energy on a overly steep lob. And so that would mean the angle is too high. So if that's the case, then we could try again with the holdback adjusted to be halfway closer to the length of the optimal launch for 45 degrees. So it probably sounds a little confusing, the description, and it is a little trickier, but it's not a lot more code in terms of implementation as compared to the static approach. Similarly, you want to cap the number of iterations, 3 to 6. You also can use the the approach of preserving the last best valid result, but the best result now that we have to define a bit differently. That's going to be which one was the fastest in the XZ plane without going over the speed limit. So if we have any that have met that criteria, we only want to replace our estimate if we find one that's better. So we don't just want to add energy in the y direction for no reason, for instance. We have this issue of needing to fail immediately if the first attempt fails, because then we don't have anything to work with. But perhaps we could adapt the algorithm similar to the discussion we had with the static approach. Now, as for that XZ vector link I kept referring to, that optimal launch, so you probably recall from like physics, introductory physics class you probably took before, the optimal launch angle is 45 degrees to get the furthest that you could possibly send the projectile. So you can figure out what that would be in the XZ plane, because you're forming basically a 45, 45, 90 triangle. And so you can use Pythagorean theorem to determine what the XZ direction contribution to the overall velocity should be. And so that's, if I go back a slide, that's what I'm referring to when I reference the optimal launch, is that length. All right, and so we can see this in action. So the 100 times shots per second metric here, we can see that the score, the stats are very similar to the other iterative algorithm, the static targeting. We've got no misses, and the count is pretty much the same as what we saw with the other. I think still potentially the static targeting has the benefits of, so the law of cosines only gives you a result if it exactly hits the target. If it's able to exactly hit the point that represents the target. Whereas we had that little fudge factor possibility with the static targeting that extends the range a little bit, because we can consider how the fact that the projectile can still hit the target without their two centers overlapping. Basically, we just have to consider the sum of the radius. So yeah, the law of cosines has a little bit of a disadvantage there, that it doesn't allow for that. And it can also, I think, potentially still throw at a higher arc than absolutely necessary, because we're only testing against the 45 degree. It might still be possible to make an even shallower angle than 45 degrees, but you can see that it often will converge on a solution that is lower than 45. So in practice, I don't think it's that big a deal, but there's probably certain scenarios where not the quickest throw is not found, and there might be a way to adjust the algorithm to actually favor the quickest to hit a little bit better than the current algorithm works. So in terms of pros, it finds exact solutions for moving targets. It might miss solutions near the limits of range, perhaps, and it may not perfectly optimize shots for maximum speed with the lowest angle, therefore meaning the soonest intercept. The way that we're refining it could, in some situations, not stably converge, and this would probably be similar sorts of problem areas that the other algorithm has, like a near a change in distance, so closing distance and then increasing distance, like point of closest approach, or perhaps if you have different derivatives of motion, like if you're accelerating such that you're getting closer and then you're getting further away again, that sort of thing. So around those areas, you might run into trouble. Also, a target that is initially unreachable but will be reachable in the future can create implementation difficulties, because the first attempt to hit the target might be an issue, though it's less of an issue with than with the static targeting, because this actually does take into account the motion of the target. So this would be like if you're approximating some more complicated movement, that it would be a big deal. But yeah, I mean, you can see that just in terms of the numbers, like at least as long as I ran the simulation for the two, they're both getting very close to the same rate of hits for the configuration. So I think they're both pretty useful. And also, this doesn't work if you have any. Well, you can only use the constant velocity with this method. You might be able to revise it, perhaps, to break up movement into like small segments. That so like, let's say if you have non-zero acceleration. I haven't looked into that at all, but you can only use a simple kinematic movement for your target, and then the projectile is you can use it with gravity, and I guess probably you could also have more complicated movement for the projectile, provided that you could directly solve it. All right. So lastly, I want to mention the other iterative approaches. So I said before that sometimes you can't directly solve the kinematic movement equation for either your projectile or your target, and that means you have to model incrementally the like position and state for based on current timestamp, and then some small delta t to the next timestamp. So um, you have to simulate the stepwise way, and so that is adding some complexity to trying to figure out, well, how are you going to aim your projectile based on these movements. So in that case, you need a way to actually simulate the projectile movement on this incremental approach, and we have to figure out how close it got to the target. And this might involve both the projectile and the target moving. So you gotta basically, it's like keeping track of a timeline in space. So for each of those little delta t's, you have a new position. So like lots of little line segments, like a path is stored in space, and each of those has a timestamp associated with how much of time has elapsed in the incremental simulation. So you can figure out how close the two paths got. And the idea is you want those to you want to refine so that they converge. So you start with some initial guess, and then you refine by dividing. So it's actually conceptually kind of similar to what we saw with the law of cosine's incremental equation. But we need some bounds on this. So like we want to define a minimum and a maximum range for the simulation. And this is covered in the Millington Artificial Intelligence for Games book. If you're interested, you can check it out. Often you might start with an initial guess that's approximated by using a kinematic equation that can be solved directly. So say omitting drag, for instance, that would give us maybe a starting point, and then we could find the bounds by maybe the maximum possible range without drag, and then knowing that drag would be something less, and then what's the shortest shot we could take, like firing straight down, or just the wherever the launch position is. So we've defined some limits, and then we can basically divide space. So we can say, all right, well, we'll take a half step back or a half step forward, and so on, kind of back and forth. We're doing a similar thing with the law of cosine's incremental approach. So that just kind of high level gives you an idea, but it's a lot of brute force computation to make this work. And it would probably be worth it if you had like maybe a very realistic war game where you have maybe some ballistic trajectories that you want to really be accurately simulated. All right, to wrap up our look at ballistic projectiles in games, we're going to consider some practical issues that come up when you're trying to implement these algorithms. So just writing the algorithm itself is really pretty straightforward. There's not a lot to it, especially if you already have the algorithm defined for you. What is a challenge, though, is actually putting it to use in your games. And it's really going to vary with your game how this works. So at the end of the lecture, there's going to be a separate video that's going to have a little hands-on demonstration in Unity, something I wrote a while back that has a character that throws grenades. And so one of the things I had to deal with in implementing that is, well, the projectiles aren't just launching from some random position like in the shooting gallery that we saw in the previous examples. I want the projectile to look like it's being thrown by a character. So it's an animated 3D mesh character. So it'd be pretty obvious if the grenade is just like flying out of his chest or his head or something. I want it to come from the hand. So that's straightforward to figure out, where the hand is. I can just attach something like a position I can track relative to the hand that's available to me in the in the game engine. And I can also measure where I am in terms of the animation. So that with an animation callback, I can say, okay, well, this is the perfect moment for the grenade to be released. So the animation system says, hey, the hand is in just the right position. Now it calls my callback, and that's when I can spawn the grenade to like go flying into the air. So that's all easy, but the problem is think about in terms of your agent deciding it wants to throw. So it's decided it wants to throw, but it can't throw yet because it relies on the animation of throwing for the grenade to actually be released, and that's like sometime in the future, very short time, but it's in the future. In my case, it was like I think a quarter of a second. That's how long it took for the character to wind up, get the hand over the shoulder, elbow forward, and then start to do the release. So the release point of the throw, quarter of a second in the future. So that meant that any sort of prediction I was doing had to be delayed. So in terms of trying to hit a moving target, in this case, there's a minion that's running along and I want to hit it. I have to do the prediction delayed start. So that added some complexity that took a bit of work to deal with. But also predicting where that future position is more than so my character can run around while throwing. So I have to extrapolate where the character will be in a quarter second while running, and then where the hand will be relative to the character, and the character can kind of lean left and right. So I tried to come up with an approximate way to deal with that, just based on like the average running speed of the character and where the hand is relative to the root of the character, which is down on the ground in Unity, the root position. So it's actually projected from the hips down to the ground. So it's the bottom of the capsule collider that's sliding around. So that took a bit of work to make sure I got that set, but it's still not perfect, especially as we'll see when we discuss some further things that are good to do. All right, so yeah, dealing with animations adds a lot of complexity, even though the throw algorithm itself, or the calculation for the trajectory, is very straightforward. It's just a few lines of code to implement. But in order to actually get to the point where I can call it, took a lot of setup to deal with throwing from the hand. It's delayed from the animation. All right, so you might also consider some gameplay sorts of situations. In the shooting gallery, we just shoot all the time at a very high rate, and there's not like an ammo limit. It's not even a game, it's just a little demonstration. The agent, though, in your game, so whatever game you're implementing, might have like valuable ammo that needs to be used sparingly. So in that situation, we don't want to waste, like say you only have a couple grenades, you don't want to waste them. So and it could also be that like whatever the animation is that for launching or throwing the projectile, like it might be a gun that takes a really long time to load, even if you have a lot of ammo. So the agent just can't be shooting at low probability shots. So we can implement a heuristic for deciding when to throw. Don't throw if conditions are bad. You want to consider things like, well, is the target at top speed? If the target is not at top speed, it's probably accelerating, because in a video game, if you're not going full speed, you're probably accelerating towards full speed or decelerating to a stop. So it's usually very little in between. So that makes a good heuristic. If the target is turning, it's probably turning to a new heading. It's not going to just keep turning all the time. It's going to turn and then it's going to run straight at whatever the next thing it's going at is. So if it's turning, just hold off. And if the target happens to be on a nav mesh, you can check to see if it continues on its current course. And let's say you solve a t value for collision. So you could say, all right, with the current position of the target, we're going to extrapolate from there, just assuming like constant velocity. Well, if that hits the edge of a nav mesh, then it probably isn't going to continue going that way because it would run into a wall or something. So there's no point in trying to throw there because then you're just going to hit a wall. So you can raycast along the nav mesh to figure out if by the time your throw would get there would hit, then that means the agent or target rather is going to move. And you can just say, well, I'm just going to lay off. I'm not going to have my agent throw. You can also check if your projectile is predicted to hit something sooner than the target intercept time. So you could say, just simulate throwing it and see if you get an intersection of the line that's formed by the throw. And then lastly, you can consider, well, do you know your target's goal? If it's like a human player and they're trying to go grab the pot of gold and your agent is throwing bombs to stop the player from getting there, well, you can anticipate that the player is probably headed towards whatever the location is, like the pot of gold. So there's lots of heuristics you might consider that will influence the throwing behavior. So as for dealing with the whether a projectile is going to hit something else before it hits your intended target, well, often you're going to have to deal with lobbed projectiles, which are under the influence of gravity. And so that means you can't just do a simple raycast or a single raycast at least. But you probably also don't want to calculate this, the intersection of this complicated curve equation with all of the different obstacles that it may or may not hit. We would really rather stay linear if we can, because we're trying to maintain real-time performance. So what you can do is you can approximate the parabolic arc. You can calculate what the peak is of the arc, assuming there is one, because your agent might be throwing straight down if they're up high or something. So you'll have to check for that. But if there is a peak that is reached, we can solve that, and we can raycast to the top of the arc, and then from the top of the arc down to the target. If we don't get any hits on either of those two raycasts, then that means it is unblocked. We might try to break things down further, because just breaking it into two raycasts, you will be well under the parabola shape. So you would say miss hitting something that actually would collide, that would be above the line. So that may or may not be a problem for your game. You could break it into, say, 4 segments and get something much closer. Or how many ever segments is important for your gameplay. And one other thing is you could perhaps in your games allow projectiles to bounce. Oftentimes they just blow up as soon as they hit anything, but maybe it's like a grenade that will eventually blow up, and you could actually skip it to the target. So that would be some added complexity to modeling and prediction if you were allowed to skip the projectile rather than having to stay in air the whole time. And then also we all of the approaches that we looked at least in detail, the agent was always throwing at full speed. But what if you could have the agent throw at different speeds? And I think most games that do allow this don't actually calculate for arbitrary adjustments to speed. They might calculate once for full speed, and then once for like medium, and once for low. So we have like these 3 different hard-coded levels. And so you're not actually considering all variations between. All right, and so lastly, there will be an additional video as part of this module that'll show much of what I've talked about in action. It doesn't work perfectly, but I did try to implement some of the heuristics that I just talked about. In this video, I'm going to give a demonstration of a little example game that I built that has some prediction for both agent movement, trying to head off a target, and also projectiles that are thrown that will use prediction as well. So let me switch over to my screen share. So I've got this little world that's familiar if you've taken the video game class, and I've shown this example in that class as well. So I'm going to start off. I'm going to show you an agent running using some simple steering behaviors. Just going to run from different waypoints, and then at some of the waypoints, a projectile will be thrown with just static targeting. All right, so we'll start off. The agent's going to run to a series of waypoints, the blue or purple squares there, and throws a grenade to blow up the crates. So since the target's not moving, I can just calculate a relative position vector, and it's not even accounting for gravity on the projectile. It just throws forward slightly high, always the same for that particular throw. Then when we get to this last waypoint, the agent stops and just, you can see, is looking at this rather annoying minion. And so next up, I'm going to configure the game so that we'll chase after the minion. Right, so I'm going to change some settings here. So we're going to skip to go straight to the minion. But now, rather than just looking at the minion, the agent is going to chase and try to tag the minion. And so I think these are the settings I want. All right, so I'll hit play here. So again, the agent is trying to tag the minion. Very difficult to pull off because the minion is so fast and the agent is not fast enough to keep up. So let's see if we can fix this problem. I'm going to enable pursue style prediction. So if you've seen the steering behavior lecture, let's see, where is it? So this use minion prediction that I'm toggling on now will allow the agent to make a better decision about where to go to. So you can see immediately there's an improvement in the agent's ability to track down the minion. It's doing a rather good job here. I'll miss that time. All right, so we might be able to improve things even more if we allow the agent to throw a ball. So I'm going to turn on throw at minion. So he's still able to tag the minion. And sometimes he gets lucky because the grenades stay on the ground indefinitely. But his throw is not very good. He's pretty good at tracking the minion down, but when he finally gets close to throw, he's throwing way behind and not high enough usually. So there's no prediction on the throw. That is why this throw looks so bad. So now we can turn on some prediction, and this is a law of cosines implementation. And it is, if you've seen the lecture on projectiles, this is the cheating version. It just adjusts the y as necessary to make the throw work. So it adds energy to the throw. I do have, so you can see that the throw is working a lot better now. It still misses because it's based on assuming zero acceleration or constant velocity of the agent. Sometimes that's a good strategy, and other times it's not a good strategy. There's a few other optimizations in the code as well. There's some heuristics that are used to decide when not to throw. It doesn't work all the time, but I did attempt some of these optimizations. So one is that the agent will not throw if the minion is not close enough to max speed. So that is a heuristic used to determine whether the minion is likely to be going full speed or not, and it's easier to perform the extrapolation in that case. Another is the minion is tested against the nav mesh, so extrapolating position to see if there's a collision. So the agent will actually hold off on throwing if these various heuristics aren't met. And there's one other I tried to implement that ends up not working as well as I'd like. I probably need to revisit this example. And that is I attempt to do a raycast according to the parabolic arc of the projectile. So I cast a ray up to the top of the parabola and then down. And the problem with that is when the agent is running around and tilting and moving, you actually have to calculate ahead to where in terms of the animation the agent will be and where the hand position will be. And that's where you actually want to cast the ray from, because the throw doesn't occur until the animation can complete, which is around 1/4 of a second. And a lot can happen in that amount of time. One last thing I want to show is just rather than running all over the place, the agent can try to throw from up high and save some effort here. And this makes things a lot more efficient. You can see some cases my raycast is failing there. It's probably picking the wrong position to be throwing from. But even so, the agent can do a pretty good job here. Those crates are getting in the way a little bit. Gotta let them clean out a bit first. He has some problems hitting the lip of the platform he's standing on, but if the agent's far enough out, it's not too much of a problem. All right, so anyway, that is a demonstration of like a more practical sort of scenario with projectiles and some more elaborate sort of tests that are necessary for gameplay purposes.